All right, so hybrid orbital theory looks at how we create hybrid orbitals to help us explain these bonds that we uh, create using atomic orbitals. So we're going to use the example of um, carbon and hydrogen bonds, hydrocarbons. And so we're going to first look at this energy level diagram for carbon. So it starts off with, we're just going to look at the valence electrons, so 2s and 2p. So carbon has 2 electrons in the 2s, and then 2 in the 2p, 4 valence electrons total. And so what we're going to do is we are going to take and promote this electron here. So this is, we're going to promote 2s electron to the 2p. And so what we get is 2s now has 1 electron, and the 2p has 1 electron in every orbital. So we now can make 4 bonds for carbon because we have, again, we have to have 1 electron in every, only 1 electron in every atomic orbital, so we can overlap those based on this valence bond theory. And so if we look at, for example, CH4, I'm not going to do anything with, I'm just drawing it, not trying to be really correct. So we have, so what you're going to do is to determine how many bonds you need to hybridize, you're just going to circle the number of electron groups. And so we have 1, 2, 3, 4. So 4 electron groups. Now electron groups can be a single bond, can be a double bond. Oh, let's do this in order. Can be a double bond, can be a triple bond, can be a lone pair. Okay, so those are all accounting as electron groups for hybridization. So if we have 4 groups, we need 4 hybrid orbitals. Okay, so 4 hybrid orbitals, if we do that, so we're going to go back to this right here. We'll redraw it and then show how hybridization works. So for this is again for carbon, 2s, 2p, so we have 1, 2, 3. So 1 electron in the 2s, 1 electron in each of the 2p, and we are going to hybridize based on the number of electron groups we have. So we're going to hybridize, and because we need 4 groups, we're going to hybridize all 4. So we're going to hybridize 4 hybrid orbitals, so 4 electrons. And what that's going to do is if we look here, I'm going to show that this is the relative energy levels of the 2s and the 2p that are our hybrid orbitals are going to be an average in between those. So we're going to make 4 orbitals. We're going to put 1 electron in each, and we're going to call these this orbital. We're going to call the 2s1p3 hybrid orbitals, or often we call this 2sp3, or sometimes we can say sp3. The 2 is saying what quantum number we're hybridizing. For carbon, there's 2. We don't have to put the 1 there. It's assumed to be 1, so we use 1 s orbital right here, and we use 3 p orbitals, so it's sp, and then 3 is telling us how many of the p's we used. So what we do, what this looks like, is we have carbon. It has 1, 2, 3, and 4, and these are all going to be sp3 atomic orbitals, hybrid atomic orbitals, and each one is going to have an electron associated from carbon. And then every hydrogen is going to overlap. Now hydrogen only has 1 electron, and it only has it in 1 energy orbital. So hydrogen comes in, and puts its, so these are the 1s. 1s. So when you're overlapping atomic orbitals, they don't need to be the same. So you don't have to overlap an sp3 with sp3. It's just that if you, for carbon, all of its atomic orbitals need to be equivalent. And so we do that by making equivalent hybrid atomic orbitals or hybridized orbitals. And what we would then say is that we would say that carbon is sp3 hybridized. Okay? And anything that's tetrahedral as a tetrahedral electron geometry. So electron geometry is going to be paired up with, or matched up with hybridization. So if you have an electron geometry of tetrahedral, you are always sp3 hybridized. Okay? Now we can continue on with this and say, okay, let's do carbon with a double bond. So let's say we have carbon, carbon double bond. Okay. What we're going to do is we're just going to focus on this part of the molecule, and then we just add in our hydrogens. Okay, so if we look at this this carbon, it needs to make 1, 2, and then the double bond counts as 1 electron or group. So we need to have 3 hybrid orbitals because we have 3 electron groups. Okay. And so we look at the carbon. We're gonna go back and draw this where we've already promoted the electron. So for carbon, it's 2s, 1 electron, 2p, 3 electrons each in their own atomic orbital. And now we're gonna say, okay, well we need 3 atomic orbitals. So we need 3. So we're going to always take the lowest energy, 2s, and then 2 of the 2 P's. And so when we hybridize those, so we hybridize, and we look at the, just to remind ourselves that the energies of the S and the P, that we have now 1, 2, 3, 2 sp2, and still 1, 2, p. So we have 3 electrons that we hybridized, and then this electron stays in the 2p orbital. It remains unchanged, and that'll actually be important for the forming of the double bond. Okay, so that's going to be our sp2 or 2sp2 hybridized orbitals. And so if we look at this particular carbon here, so we have a carbon, carbon, and then so this carbon has 3 sp2, sp2, sp2 orbitals, and then it's going to overlap this. So this carbon, if I just draw the whole thing out, it's just a mirror. Also sp2, sp2, sp2. I'm really just focusing on the left. So then now the hydrogen comes in, and we have, this is a hydrogen 1s, hydrogen 1s, and then over here, same thing. And then putting in the electrons for the hybridized sp2. We have our bonds. Now, that takes care of all the bonds, and this is a good point to mention that the types of bonds we have, any bonds that form along the internuclear axis, which means if I can draw a line between 2 nuclei, so 2 carbons, a hydrogen, so this is what we call an internuclear axis. Then if a bond's symmetric about internuclear axis, we call that sigma bond. So we have this would be a sigma bond here, sigma bond here. This would be a sigma bond here, sigma bond here, and the last one here. So all of our single bonds are going to be sigma bonds. Now, we've taken care of these three, but how about this 2p? And so this is where the double bond comes in. If we look up here, we have a double bond. So single bonds or sigma bonds, our double bond is going to make a pi bond. A pi bond comes from the p orbital. So remember that these p orbitals, we'll do them in green, are still hanging out here. These are our 2p orbitals. 2p. Okay. Now, we're not going to have direct overlap like we do for sigma, and that's important. What's going to happen is that these two are going to basically make, I'll draw it, I like to draw it like this, but what a lot of people draw is you're going to have your carbon-carbon sigma bonds, but then your pi bonds are basically going to be like an electron cloud above and electron cloud below. So this would be one pi bond that represents both top and bottom, and then this would be a sigma bond. So your double bond, let me actually do this, would be, I'm just trying to show it with colors. You have your single one, your first bond you make is a sigma, and the second bond you make is a pi. So we represent these kind of like electron clouds with, I just kind of draw in the p orbitals and then do those kind of lines connecting the two, showing that they're going to overlap. It just kind of helps, makes it a little messy. Okay, now this is just to kind of give you an idea. Your book also has really good pictures here. And then just to finish it off, we can do a triple bond to go along with carbon. So that would be a carbon, triple bond carbon. Okay, and in that case, we're going to have just two electron groups. So two electron groups, which means we need two hybridized orbitals. So if we go back to the carbon, carbon's got that 2s, and then the 2p with a promoted electron in this last spot. And because we need two, we're just going to take one of the 2s, always the lowest, and then one of the 2p. And so when we hybridize, we are going to get two of our 2sp, one of the s, one of the p. And then we still have our 2p, we still have our two electrons that were not hybridized, still there. And as you'd imagine, if we look at our carbon, we're going to have those two hybrid orbitals. This is our sp, sp. And now our hydrogens come in on either side. This is our hydrogen 1s, hydrogen 1s. Now to get our two other pi bonds, so then this is, so we have, oh, I forgot to do the, let's do this right. So let's make sure we actually have another carbon, 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 sp, and then we have our hydrogen 1s, and we got the electron here. Okay, so that's better. So if we look at the bonding of our carbons, we can then look at this one is in green, and this is our 2p. It's called 2p 2pz. 2pz because it's coming up, and that's going to make our first pi bond. And then we'll do red. Let's call this 2px, and it's going to be coming out and away, and it's going to make our second bond, kind of behind those as well. And this is our 2px. And so if we look at then our kind of schematic of this, carbon sigma's first pi, second pi, so this is one pi bond, this is second pi bond, and this is our sigma bond. So our triple bond has 2 pi bonds and 1 sigma bond. We always form the sigma bond first. So that's how we can create hybrid orbitals. And we'll talk about expanded octets and hybrid orbitals tomorrow.